this video, I want to go over part 1 of the fundamental theorem of calculus. And what it states is that if g of x is equal to the definite integral of f of t from a to x, then g prime of x, or the derivative of g, is going to equal f of x. And what's that basically saying is that the derivative of the antiderivative will give you the original function. So for problem number 1, we're going to start with g of x, and that's going to equal the definite integral from 1 to x of t squared minus 1 to the 20th power of dt. Okay, so the way we want this to look is we need this definite integral going from a constant, which is 1, to the variable x. And since it's doing that, this is going to be a very simple problem. We will come across to where certain integrals where, say, the constant is on the top and the variable is on the x, and we're going to have to manipulate it so that it is in this form of constant on the bottom and x on the top. Okay, so that's what we're going to need to do. But for this problem, it's simple. Since it's in that form, we can just replace t squared, or any t's in our problem, with x. So g prime of x is going to equal, we place x here, so this is going to equal x squared minus 1 to the 20th power. And this is the answer to this problem. So for problem number 2, we need to go about it the same way. We need to check to see if our lower limit of integration down here is a constant, and it is. And we need to see that our upper limit of integration is x, and it is. So we can go about this just like last time. We just replace t with x, and f prime of x is going to be equal to the square root of x squared, because we replace t with x, plus 4. And that is the answer to this problem. So for this one, our x is in the lower limit of integration right here. And to use the fundamental theorem of calculus, you need your variable to be in the upper limit of integration. And we can actually flip the limits of integration by changing the sign of our integral. So if we rewrote this integral as h of x is equal to the negative definite integral from 2 to x, this is now doable because our lower limit of integration is a constant and our upper limit of integration is our variable. So this is totally doable now, of the cosine of t squared plus t dt. And all we do for this is we now place x where each one of our t's are. So this is going to be equal to negative cosine of x squared plus x, and that is going to be the answer to this problem. So for this problem, we're going to start it the same way. Our lower limit of integration is a constant, and our upper limit of integration is our variable. So we can replace all t's with x squared, and we're going to be left with the square root of x squared, but we can't forget to raise it to the 3rd power, minus 4. Then we have to multiply it by the derivative of x squared, which is 2x, so multiplied by 2x. And the reason we do this is because of the chain rule. When your variable is anything other than just x, so right here it's x squared, you must multiply by the derivative. Technically, we've been doing this using the chain rule on all the previous problems, but when the upper limit of integration is just x, the derivative is 1. The derivative of x is 1, so it doesn't affect the problem. Okay, so you should remember that when your upper limit of integration is anything other than x, when it's 4x, when it's the square root of x or the 9th power of x, you have to also multiply this by the derivative. So if we simplify this and rewrote this answer, the inside the square root, 2 times 3 is 6, so this is going to be, well, we'll bring this to the front first. So we're going to say 2x times the square root of x to the 6th, because 2 times 3, minus 4. And this is the answer to this problem. So our fifth problem is going to be a little bit different. Our upper and lower limits of integration are both some variations of a variable, and there is no constant. But the good news is that we can still solve this, okay? So the way we're going to go about this is we are going to break this up into two integrals. So we're going to say, and we're going to leave the upper and lower limits of integration empty for right now. So we're going to say the square root of t to the 4th minus 2 dt plus the integral of the square root of t to the 4th minus 2 dt. Okay, so the way we're going to do this is we're going to break this up somewhere in between x squared and then some point on the function in the middle, and then we're going to integrate from x squared to that point, and then from that point to x cubed. So the way we're going to write this is from x squared to some point in the middle, which we're going to write c for constant, and then we have to integrate from that constant to x cubed. Okay, and this is how we're going to do this. So from our previous examples, you can see that the lower end limit of integration is not a constant, so we're going to have to switch this around by taking the negative, switching the signs of this integral. So this integral, we'll rewrite it as the negative integral from some constant c to x squared of t to the 4th minus 2 plus, and then this one's fine, we'll just rewrite it as is. So from some constant c to our variable x of the integral of t to the 4th minus 2 dt. Can't forget the dt's. Okay, so the way we do this, on both of these integrals now, it's from constant to some variable x. We're going to replace all t's with x squared. So this is going to be the square root, and we can't forget, we'll put a negative out here, the square root of x squared, but we can't forget we're raising it to the 4th because we're replacing all t's with x squared, raising it to the 4th, minus 2. Then we got to multiply by the derivative of x squared because it's something other than just x, so times 2x plus, if we replace t to the all t's with x cubed, we will get left with x cubed. Can't forget we're raising it to the 4th power, minus 2 times the derivative of x cubed, which is 3x squared. And we're done. We just got to simplify this. So we'll move 2x out to the front. So this is going to be negative 2x times the square root of 2 times 4 is 8, so x to the 8th, minus 2 plus 3x squared times the square root of 3 times 4 is 12, so x to the 12th, minus 2. And this entire thing is the answer to our problem. So for our sixth and final problem, we're going to have the definite integral from tangent x to x squared of 1 over the square root of 2 plus t to the 4th dt. And as you can see, the upper and lower limits of integration are some form of our x variable. So the way we're going to have to do this is we're actually going to have to break this up again. So somewhere between tangent and x squared, we need to break it so that we can integrate from tangent to that some point in the middle, and then from that some point in the middle to x squared. So we are going to write from the integral from tangent x to some point c in the middle, which is going to be a constant, of the integral of 1 divided by the square root of 2 plus t to the fourth dt plus the integral from some point c, we're integrating from here, to x squared of the same function. So 1 divided by the square root of 2 plus t to the fourth. As you can see here, we don't have a constant on the bottom. We actually have tangent of x. So in order to get the constant on the bottom and tangent up to the front, we switch the signs of this integral. So if we rewrote this, this would be negative from some constant c to tangent x of the function 1 divided by the square root of 2 plus t to the fourth dt. And then this one is fine. We have from some constant c up to our variable x, so that's totally fine. C x squared 1 divided by the square root of 2 plus t to the fourth dt. And now what we do, we have it in the form that we need. We're going to place tangent x. We're going to replace t with tangent x. And since tangent x is something other than just x, we will then have to also multiply by the derivative of tangent x. And it's the same case over here. So this is going to be equal to negative 1 divided by the square root of 2 plus, so we're going to replace tangent with t, and that'll be tangent to the fourth power. So I'm just going to write that down. Tangent to the fourth x times the derivative of tangent x, which is secant squared x. So times secant squared x plus, we're going to replace all t's with x squared. So plus 1 divided by 2, or the square root of 2 plus x squared raised to the fourth times the derivative of x squared, which is 2x times 2x. And then we need to simplify this. If we multiplied negative 1 divided by the square root of 2 plus tangent to the fourth power times secant squared x, it would be secant squared x would just go on the top. So this would be secant squared x, negative secant squared x divided by the square root of 2 plus tangent to the fourth power x plus 2x divided by the square root of 2 plus, and then 2 times 4 is 8, so 2 plus x to the 8th. And that is the answer to this problem.